Hello, everyone. Welcome to another episode of Robo Papers. Super happy to have Jang with us today. He's one of the authors of this paper called DreamGen, Unlocking Generalization in Robot Learning Through Video World Models. Maybe just a quick one on yourself, Joel, if you can.
Thanks for having me. My name is Joel. I'm currently a research scientist in NVIDIA Gear Lab, and I'm working on video world models and latent actions. And today I'll give an introduction about DreamGen, which is a work that tries to enable generalization in training robot policies through video world models.
Perfect. Cool. Awesome. So maybe as a start, if you can share screen, and then I know you have some slides.
Okay, yeah, I can go ahead. So this project started last year, October. So we started with the question of, so we started seeing video world models or like video generative models able to generate very realistic looking videos. And when we specifically image to video generation models, so when we prompted it with new initial frames of like maybe like a robot, maybe like a Franca robot, it moved the robot. And it didn't really follow language very well, but it still was able to move the robot. So the core hypothesis was, okay, if we prompt a just proprietary video generation model or any like open source video generation model with just a new action, which is like the prompt of the robot, and if this follows the language, isn't that a new verb? Like, isn't that a new motion? And if we can enable the actual robot to do that, can we extrapolate out of the teleoperation data? So that's like a core hypothesis that started this project. And yeah, so how can we enable a robot that's just trained? So this is a video of the robot trained on a single task in a single environment. And you can see that it does pretty well. It can do pick and place. It can do like some handover pretty reliably. But how do we make it do new motions in a new environment, like, closing this soup container? Yeah, so that's the problem formulation. And yeah, in this specific work, we show that we can collect teleoperation data of a single task, which is pick and place, variants of pick and place, in a single environment in the lab, and train robot policy, specifically a humanoid robot, to perform 22 new behaviors, new motions, in 10 new environments, and all without collecting any teleoperation data. So how do we do this? So like I said in the intro, this motivation started with image to video models. So we use call it video role model we take an initial frame of the robot in a new environment, and we prompt it to generate a video of it doing a specific task. The language, we input the language, and we can see that the video role model can generate a realistic looking video. And then we use this data to train visual motor robot policies. And I'll get into the details of how we do this. So this pipeline, we call it DreamGen, and it consists of 4 stages. First, we fine-tune a video role model on a specific robot embodiment. And this step teaches the video role model about the kinematics of the robot. So how the robot moves, the physical constraints of the robot, the physical joint limitations, the degree of freedom of the robot. For example, like for this specific data that we did most of our experiments on, we use a Fourier GR1 robot, and we use a 6 DOF hand. This physical robot had to really has some physical constraints in the degree of freedom of the hand. If we just natively use without this stage, then it may generate more human-like forms, but the actual hand can't really do those kind of stuff yet. So that's just one example of what this phase pitches the video world model. And in the second phase, we use a fine-tuned video world model to generate videos. So we try prompting with new behaviors. Like we only fine-tune, in stage 1, we used pick and place, but we try water the flower, which is a new motion. And we also can take the robot to a new environment and then prompt it with a seen or unseen verb as well. So these are some examples of the generated data. You can see that this video successfully waters the flower. And also this video successfully picks up the tangerine and puts it in the bowl.
I see. So even if during the fine-tune phase, the only tally op you did was pick and place, what you're saying is that it can somehow learn something way more generalizable just from the base video generation model that you're using, and it roughly know what does watering a plant or watering a flower mean, and it's then able to do it while knowing the kinematics of that robot and dream. And everything, at least in this particular screen, is pixel purely dream up, right? Except maybe the first frame.
Initial frame. Yes, yeah, that's correct. And like the high level hypothesis is that during the pre-training of the video generator model, it pre-trains on like say most videos from the web. That's when it learns the web data. So that's how we bridge the web data, internet data to the pre-training of the video generator model, where it learns all like watering flower, what that means, and everything else. And then yeah, so that's the phase we think.
How much of that teleoperation data do you need to get this to work?
So there's different scenarios we experimented on. But TLDR, like about 100 teleoperation data is pretty sufficient enough to enable, some adaptability.
Did you need to like vary the background and stuff when you did the teleoperation, or is this all just like kind of in the plain scene, like waving the arms around?
So in this specific setup, we didn't vary the background. So we only collected in the lab, but we were able to just generalize to the environments. Okay, yeah, so I can go ahead and, so in the stage 3, now we have videos. Now we need actions, robot actions. So we tried 2 different methods of extracting actions. First is we train an inverse dynamics model to extract raw robot actions. And second is we use a latent action model to extract latent actions. And then we call them neural trajectories because they're neural generated robot trajectories. And then this is just like very similar to actual real-world teleop data, just a mapping of like a observation to actions. And yeah, we can train any visual motor robot policies using this data. And through this 4-step pipeline, we focus on showing 3 new capabilities. First is augmenting training data for context-rich tasks that are very hard to generate simulation data for. For example, like tool use and like, manipulating deformable objects. Second is we can generate synthetic data for new behaviors outside of the teleoperation data. And third is synthetic data for new environment. Yeah, I'll get into detail for each. So for generating train data for context-rich tasks, so we start off with collecting 10 teleoperation data, 10 trajectories for tasks. So like, using tool use, folding, and like wiping liquid. And then we fine-tune the video world model on these specific tasks. And we generate the neural trajectories after going through the 4-stage pipeline. So yeah, you can see that these synthetic data can perform these tasks reasonably. And after that, we, in this specific setup, we co-train with real data, and we train video robot policies. And so these are some of the execution examples after co-training with real and synthetic data. But we only use 10 real data.
So this is 10 real data co-training with is 1,000 examples or so generated video traces of this task, right? So what is it using which of the 2 action representations was this with the inverse dynamics model or the latent actions?
These are using the inverse dynamics model actions.
Okay, yeah.
And we co-train with 300 neural trajectories. So 10 real data and 300 neural trajectories.
I think it's really nice that you can just kind of throw all of these into one kind of training. Did you have to do any balancing? I know like where you sample like 50% of a batch from the real data. You did, okay. Yeah.
For the daily training, we did 50.
Yeah, makes sense. And that's okay even with 10 examples. So you're like seeing like, aren't you like using the whole real batch basically every time, or is that
the training was still okay. Sorry.
Yeah, Joe, I don't know whether you have a slide later on for this, but I'm curious, like, how well does the 3rd stage, I mean, either the IDM or the latent action model, basically you're trying to infer action just based on the, I guess, ecocentric view of supposedly what the thing, right?
Yes.
How accurate are the actions? Sorry, maybe I'm jumping the gun here.
No, of course, no. That's a good question. That's like a lot of the questions that we actually received during like the middle of the project. Okay, say we generate IDM actions, how can you quantify if the actions are better and better? So one thing that we did differently from previous work, so there's like VBT and UniPy, their IDM model is pretty small, relatively small. Ours is VLA still, so it's a 2B model, and like it's just initialized from the same VLA architecture. So I think we really tried to make the IDM model much bigger. And second thing is the base video models got like better and better. Pipeline only started working after the newest models came out, which is like 1.2.1 at the time. We're like, okay, well now we're getting, so I think those two components together enabled this project to work. And yeah, how we quantified the IDM actions were actually working. So first thing is we replayed the actions. So we can replay the actions in sim with the same embodiment. We can also do that along with the generated videos. So say we have a real generated video of the GR1, like doing the pouring test. So we extract the actions. We only replay the actions because we have the same embodiment in sims, and then we can see it doing this motion. So that's one thing we can do as an intermediate step. Second thing is actually training the policies with the generated data. So what we tried was we tried only training on the neural trajectories without any real code training, but we were still getting like 20% success rate in sim. So that also meant the IDM extract actions were already good enough. But it was like, yeah, there were some gaps, but still.
Got it.
Yeah.
I see.
Yeah.
Cool. Interesting.
Yeah. So I guess let me just first go ahead. So yeah, generate synthetic data and then, but yeah, this pipeline is pretty straightforward. It's just a simple 4-stage pipeline. We can apply it to different robots and also different robotic systems. So a lot of the robotic systems right now require multi-view, and that helps quite a lot. So this specific setup is from the Droid setup. So we have left, right, and wrist cameras. So we just simply concatenate these multi-view, then do the same pipeline. And we see that the neural trajectories generated synthetic data also retains the consistency from the multi-view. So you can see as the robot moves on the left view, the right view, the wrist view, they show consistent motions.
Sorry, Joy. So which one of these are dreamer by DreamGen? Is it the right?
Oh, so the upper are the teleoperation data. We also fine tune on 10 teleoperation data for each task. So there's 3 tasks. One is just pick and place. One is cube stacking, and one is scooping M&Ms and pouring. And yeah, these are generated data of the you can see it's generated by usually it's bad at words, so the fonts are weird. Yeah.
I see.
And
yeah, I love that you mostly can't tell though. That's pretty impressive.
Yeah.
Which video model is this? Which generative model is this?
So a lot of the experiments we are using 1.2.1.
Okay. Yeah, makes sense.
Yeah. And yeah, you can see that these are generated data. Apparently, like this video is specifically can show that these are faked videos because you see the M&Ms, number of M&Ms getting much more than physically possible from the scoop. These kind of artifacts kind of show that these are generated.
I see, but again, this second row here all are imagined and dreamed up by DreamGen.
Yes.
Starting with the first frame of the sequence from, let's say, the teleop clip in the first row, something like that.
Yes.
Okay,
yes.
I see.
Yeah.
I see. Okay.
Did you have to do anything special to get the different camera views to maintain consistency? Is that like part of the fine tuning, or is it just happened?
Yeah.
So I want to also mention this. When we just only fine tune on our system, so like just 10 teleoperacy data for each, it didn't retain consistency and like didn't really follow like generate these very coherent videos that well. Yeah, it did, but it wasn't like there was still some like lack, especially in the multi-view scenario. But so in this specific setup, we pre-train with the Droid datasets, and then it helped retain the multi-view. So I think the multi-view, there's still, because the 1.2.1 or auto video models, they don't really support multi-view natively yet. And so there needed to be additional adaptation phase. With the Droid, it's a lot of data, so it actually helped.
Did you actually just like, when you did multi-view, did you end up, do you like query it to generate like one very large image with different images in it? Or are you actually like...
Yeah.
Like, okay,
this,
yes.
this is it.
All right.
It
So just
generates,
like this, basically.
yeah, this is the actual video it generates. Yeah.
Okay, that makes sense. Yeah. And Droid, did you need to do anything? Like Droid is obviously, this is the robot from Droid, so you would need another similar data set like that for your to test on your Fourier, like FR, or sorry, I forget his name, the Fourier robot. Or do you, or is this like enough for to get that for the humanoid as well?
So we haven't tried
Okay,
multi-view for humanoid.
fair enough.
That's a good question.
But so you're saying that, I mean, this I suppose that, you know, a wrist camera and then maybe like two other angle. And what you're saying is that they were basically physically non-coherent until you take the entire droid. So how big is the whole entire droid data set again? Do you remember?
I think it was like 50K trajectories that we used.
Interesting. So even just with that 50K, somehow DreamGen has figured out what is the, because it seems to me way harder to do than just like simulating one frame. Right now, like 3 views have to be consistent. Right?
Yes.
And how do you gauge the consistency right now? Do you just look at some individual and then,
human eval for now. Yeah.
okay, human eval, yeah, because I imagine extremely hard to. Interesting. Okay, got it.
But this is a good like a research formulation where how do you quantify the consistency of multi-view generation?
Yeah, I suppose if you do the whole thing in simulation, like you can tell you in simulation, but because in simulation you have ground truth, then you can probably really scale this up and get the multi-view thing.
Yeah, that also makes sense too. Yeah.
Okay. Interesting. Sorry.
Yeah. No, that's
Yeah,
good.
okay.
Good. Yeah. Yeah. So we do the same pipeline. We train row policies to perform these tasks. So just like cube, I don't know, milk pick and place, cube stacking, and scooping M&Ms. So these are all co-trained with real and neural trajectories. We applied the same pipeline to a $100 robot, which is the S0100, to show that this is a very scalable, like it requires minimal effort to set up the whole pipeline, and works with like egocentric camera with a cheap robot as well. So yeah, generated neural trajectories are very realistic looking, and yeah, it actually helps the visual robot, the visual motor robot parts as well. So just the neural trajectories are just synthetic data, which can be applied to other just any kind of robot policy. So in this experimental setup, we use diffusion policy and pi0 and grid M1 as the robot policy, and we show that it results in consistent performance enhancement for 3 different robot, which is the GR1, Serial humanoid, and then the Franca robot, and also the S0100.
Yeah, I remember the first time when we kind of taped this episode, we went into this a bit more detail. Could you talk a little bit about like what are the toolbars? And it looks like the light blue one usually is slightly better, but then except for maybe the one for hammering. Anyway, could you talk us through a little bit more?
Yeah, of course. So low data is usually 10%. So what we did was, okay, so say we collect for a single task for hammering, say we collect like 100 teleoperation data, and then we train the policy, and then it works. Okay, that's our sanity check. Okay, now if we have 100% of the data, now it works. Then we sample 10% of that. So that's the low data results. And then we augment the low data with neural trajectories, and then we co-train it. So that's the blue bar. So yeah, those are the 2 bars. And one thing to note is a pretty detailed thing is that the generated trajectories, neural trajectories, when we do the IDM phase, we don't extract the robot state or the robot perception yet. So, and diffusion policy and pi0 don't natively do anything else to the data with 0 states. It's co-trained with data with perception and without perception. So sometimes that results in like performance degradation, as you can see in the diffusion policies for hammering. And that's why the delta isn't that high compared to Grid M1. But Grid M1 has a concept called embodiment tags, so it has different parameters for different embodiments. But what we do here is we treat neural trajectories as a different embodiment during co-training, which helps I think the negative transfer that comes from the zero proprioception. Yeah, that's just a detail.
So basically, tasks where proprioception was really important, like hammering, it did not do as well at. So that's one of the that's kind of that's what you're saying, right?
Yeah, I guess that's trend limitation.
Yeah. And you could solve that by like having this data trying to estimate the proprioception maybe or something, or maybe it's just a limitation because it's hard. Okay, that makes sense. And the other one that's really interesting to pull out though is I think Michael called this out last time before our call failed, was the tic-tac-toe example in the bottom left where the neural trajectories make a tremendous difference compared to everything else, right? Did you want to comment on that as well?
Yeah, I guess this also the tic-tac-toe right now in this specific task. So the human places the X, and the robot picks up the circles and then puts it. And there's 9 different candidates of the action. So there's 9 possible places the robot can do the place action in. And I guess when we downsample to like 10%, or I think this specific setup we downsample to 25% because like, it's a little bit a harder task. So when we did 25% in the low data, then we lose the other, possibilities that it can go. Like maybe it might, in this specific configuration, it might not have gone to a specific square. But using the neural trajectory, you can actually cover all the counterfactual, possible features that can help, especially in this specific setup where, the motions might be relatively easier to get a high performance, but you really gotta cover all the counterfactuals. Yeah, so I think maybe those scenarios, this pipeline can benefit quite a lot.
Got it. It's interesting to me, I guess, that then therefore what you're saying is that for certain tasks where maybe diversity in outcome and scenarios and environments matter a lot, and this is where your neural trajectories your dream scenario will help a lot.
Yes.
But for certain tasks, perhaps, I don't know, let's say for maybe stacking, or actually most of these, it may not actually help as much. Or do you think it's just a matter of because you're doing it at research scale, you haven't really pushed the boundary of world models yet? Like, for example, what's this one? Scooping M&Ms, right?
Yeah.
If you were to do way more neural trajectories, could you have done better? Or you think it's still kind of limited by something else? Like, can you dream your way out of this? Is what I'm saying.
That's a good question. And I think also in the scooping M&Ms shows the least performance increase. And also, like, I guess we didn't really diversify them. It's a single task also. Like maybe the tic-tac-toes we can consider multitask. And maybe like, yeah. But I think that's a question remain to be explored, whether we can really push the dexterous task performance, I guess, or just like in the motion side, not only the maybe the counterfactual language following side. Yeah, I think it depends on how strong the 2 components are, which is like the video run model and the IDM model. So I think if we try to scale and while quantifying those 2 axes, there's potential to get there.
I wonder if it's also maybe the specific way you literally prompt the DreamGen to dream up, right? Because your prompt basically limit the exploration space, right? Like, for example, maybe here you just tell it to, okay, pick up the M&Ms. But maybe if you are a little bit more descriptive, or maybe like, or literally you say, hey, pick up the pen in the creative way, and then therefore it do more stuff. Do you think it's also like kind of bounded by the way you prompt?
Yeah. And that also means is bound by the video role model. I think currently that is the case. For example, like if I say prompt the model, pick up a single M&M while we fine tune on data, while you just picked up all it won't be able to be precise enough to pick up a single M&M. That's a very it doesn't follow language that well. But that also means we can quantify how much lacking the video role models are. So there's probably ways to enable that capability. Maybe it might be just having a better base video role model that can follow precise language very well. That might be the case. Or maybe there can be like post-training strategies. Right now, as default, we do like LoRa training that actually helps during the post-training of the video role model phase with that helps not lose raw knowledge that I learned and then still adapt to the robot kinematics. But there might be more, fancier approaches.
Yeah, so I think this is really interesting because so one thing that I was wondering about is with these image generation models and video generation models, because you're actually using just a general purpose video model in WAN, not like a robotic specific world model, but like those things are tend to be pretty bad at making like really small adjustments, move 2 centimeters to the left or something like that, and really good at semantic adjustments, like placing, like your tic-tac-toe case, like filling out a board differently, right? Like predict. So like, does that have any ramification? Because like that makes me think like that does kind of look like what we're seeing here, right? Like where like it's not quite as good at handling the hammer and case, or presumably it's not as visually distinguishable, not as, I don't know. Yeah.
Yeah, I think maybe the first step is to start the quantification of like,
Yeah.
and a lot of the video generation field are quantifying like physics following like physics alignment metrics. I think making improvements in that can actually lead to stronger results. As in the later presentation, I'll give some intro of the DreamGen bench aims to quantify that as well.
Mhm.
Okay, yeah, maybe I can go ahead and then go on to the 2 other contributions. I think it's oh yeah, and we also show the same pipeline in simulation, the Robocasa benchmark, so that's replicable, and also instant we can do different experiments like in a larger scales. And we generate 240,000 neural trajectories using the same pipeline, and we assume we're in a different data regime scenario. So the blue is like a low data regime where we have like lower number of rural data for the whole pipeline. And then like mid data and high data regime scenarios. And in each scenario, when we scale to 240,000 neural trajectories, we see a consistent trend of increase in performance. Yeah, for both IDM models and latent action models.
Yeah, I maybe this is just an observation of mine. Right now, currently, the way I think about world models, I think of them as simulation, but a different way of unlike let's say the Robocasa, right? Which is one is very deterministic, the other one is very maybe literally dream out. And so it's like you take a classical simulation with this new class of data driven simulation, and they play along with each other and augment. It's kind of like that. So doing a lot more in the classical simulation get you that from blue to yellow, and then throw up a world model, it gives you further. So I think that's quite interesting.
Yeah.
This is actually one of the things that I thought was most interesting and different about DreamGen, actually, is that you're not doing the full like classical like data-driven simulation thing where like I give like a continuous control action to generate the trajectories or something like that, right? Like in Planet, or I don't know. You are giving higher level language commands and then working backwards. Yeah. It's actually like notably different from like what like the like navigation world models paper did, where they were giving trajectories, or the 1x world model, same thing, right? Which I think is maybe we can save that discussion for the end, but I do think it's an interesting one. Like,
that's an interesting
one. What are the ramifications of that, right?
Yeah, in terms of like data augmentation, I haven't really thought of, because like that's the action condition and this like text condition. Yeah, that's a good distinction. Yeah, good to ponder about. Yeah.
And sorry, can I just ask, so for you to get, let's say, the 240,000 is the same text instruction, but then you just generate 240,000 of that text one text instruction, right? So you haven't play around with like generate different variation of maybe similar text instruction.
Oh, okay. In this specific setup, the Robocasa has a diverse, like it doesn't comparable to other robot datasets. It doesn't have, it's like 24 different tasks, and each task, except the variance of pick and place, has diverse language. For example, opening, closing doors is pretty like open or closed, like that's it. So we didn't really have to diversify the language there. Yeah, and for pick and place we did, but there's we had to get the initial frame somewhere. So we get the initial frame from the sim environment, and we can randomize the sim, get some, what the target objects are. So that's how we got the language there. Yeah.
Got it. I see.
Yeah.
Okay, cool.
Yeah. So in the next 2 contributions, we focus on showing generalization. So so in this specific setup, we fine-tune the video world model on about 3,000 teleoperation data, a variance of pick and place in a single environment, which is like the lab setup. So like these are all teleoperation data of pick and place using like left or right hand, pick something and then placing somewhere. And yeah, now we prompt the model with new verbs. So these are some generated data with some new prompts. So you can see, you can open the MacBook, unrolling the math, piping, pressing, watering, closing the microwave, ironing, and yeah, lighting the candle. And what's interesting is that there's fire here. So, it's synthetic. Yeah, so what we do in this specific setup is, okay, so let's say we want to do this task, open the MacBook. Then we actually take 50 initial frames in the real world, and we randomize the MacBook location. So, okay, so we want to do train and eval on like this square. So we randomize the MacBook location across the randomized area, and then take 50 initial frames and then go through the pipeline, generate 50 neural trajectories, and then we train the the role policy only on the neural trajectories. In this setup, there's no co-training with real data. And we show that this can enable us to enable a robot to perform these tasks. It's like opening a MacBook, and it's like ironing, unrolling the mat. It's like new motions outside of teleoperation. So it's like it's just like pouring motion. And as you can see, it's still quite a lot jittery because we only train on the neural trajectories and is with zero proprioception. So you lose the proprioception information, so naturally it becomes more jittery. Next, we go to new environments. So we take the robot around NVIDIA, like the NVIDIA kitchen, the cafe, and we prompt in the left for examples of scene verbs. So it's like variants of pick and place in a new environment, and these are variants, new environments but new verbs. And we can see that the video model is able to generate realistic looking videos and perform the task. Same thing, we train robot policies to do these pick and place in a new environment. New verb, lifting the bucket, and closing the soup container. Yeah, so to show those two contributions, we had to come up with, take some initial frames, come up with new prompts, take the robot around new environments. We had to do this whole pipeline. Some worked and some didn't work. Like I showed examples of what worked. And a lot of the examples, it didn't follow the language, maybe, harder emotions and like new environments. So if some failed and some, so we were like, okay, let's make a benchmark out of it. So now we quantify the ability of the video generative model to follow language on like manipulating novel objects, like new behaviors and new environments. So yeah, we quantify existing video world models. So the zero-shot variants and also the fine-tuned variants of the models. And yeah, we show that zero-shot models are pretty bad, the open source versions. And yeah, this is pretty outdated video slides, but the Cosmos Predict 2 gets the best score so far in this benchmark right now. So we also show that the DreamGen bench scores actually correlate to the robot policy results. So as we get better video world models, that will enable stronger robot policies. Yeah, so we released the code for the entire pipeline, like fine-tuning Cosmos Predict 2 and training the state-of-the-art IDM model, as well as extracting IDM actions and converting to LeRobot to train any VLAs that can natively support LeRobot. So yeah, the whole pipeline is open source. And so yeah, feel free to check it out.
Yeah, sorry, Joe. Could you go back to the previous slide? So you mentioned something about like this. Cosmo. Okay, so Cosmo is here. So this is something you're saying is probably one of the better ones now, and
Yes.
because it's scoring pretty high on DreamBench score, and therefore the actual policy that you train from that is getting a decent score, RoboCasa score. What is a RoboCasa score? Is there like a theoretical limit? Like what does 20 mean?
Okay, so the RoboCasa scores here are the average of the 24 tasks. And in this specific setup, so in the RoboCasa experiments I showed before, we co-train with real data. But to really quantify how good the neural trajectories are, co-training leads to the best performance, but only training the neural trajectories is a better method of quantifying how good the IDM actions are, how good the videos are actual for the policy. So these scores are only trained on the generated neural trajectories. So these are the average of the 24 tasks.
And these are percentage success rate. Is it so 20? It's average 20%. Okay, got it. I see. Do you see a path where just dramatic increase in capabilities of these video world model that you can just just do that? Like, do you think there's a limit? Like, would you be surprised if it hit like around 80, 90%, or even closer to 100%? Just having a better Cosmos.
I think right now that also depends on the specific eval. Right now, RoboCasa requires left to right wrist view to actually get higher numbers. That's how the benchmark is formulated. Hence, yeah, I think that might be the bottleneck. Because but all the base video role models right now don't really focus on multi-view generation. So it depends on I think maybe other benchmarks we can kind of expect just the base video role models to get better and better. Maybe like a single egocentric view. Yeah.
Yeah, I guess what I'm trying to get your thoughts on is obviously no one can predict the future, but what's your gut feel about how far we can stretch this paradigm, right? I mean, I guess the appeal of something like a world model is you get all this. Well, first of all, right, I mean, awesome work and some really really cool demos here. Like, and it seems to me you genuinely have a lot of fun doing this project. Unlike some of these other researchers that we talk to have a lot of pain because they're dealing with teleop,
Oh, yeah.
just extreme painful. So I think everyone will probably want this to kind of work. Meaning just a better video world model. We can drill out the whole thing.
Yeah.
And then hopefully eventually everything's zero shot. But do you see some limitations? Like how far? Would you be surprised if it can't even hit 80 or 90% on RoboCasa, right? As you have better.
That makes sense.
What's your sense? Yeah.
So I think there's so I really a good point on the me having fun, because when I talk to a lot of my friends in like robo learning community, like a lot of people, especially dealing with sim, they do have a hard time like setting up the sim like environments, and like there's a lot of manual efforts. But like this pipeline is much easier because we just prompt and we just fine tune. Like that's it. Like so I think it requires less domain expertise compared to like other approaches. But I think there are just inherent limitations, especially in the physics following. So the video models, like they're getting better and better, following better physics. But still there's, I guess a lot of people test the video generated motion, like doing Olympiad stuff. They're like flipping and they're putting like diving into the water. It's getting better and better. But still, I think just with the current paradigm, we might need something else to really align it with physics. Maybe Sim can help on that. I think a lot of people are currently working on that direction. I think once that is unlocked, I think it can, but which will, people are naturally pushing for it. So I think there's got to be progress. It can unlock further and further. Not sure where the ceiling is.
Do you think that there's anything we should be concerned about with it? So like in this case, like Juan is basically, or your video generative model is basically solving the robotics task to generate the data, right? So do you see any case where it won't be able to do that? Like, maybe because like the robotics data doesn't exist, or because like the robot kinematics can't be handled or something? I don't know. What do you think? Or is that just not like the right place to be? Maybe you just don't use this for that kind of task. I don't know.
So I think very precise tasks that really requires maybe like tactile sensing, like or like insertion.
That makes sense. Right.
I think insertion.
Okay. Well,
but
didn't you do some insertion? I guess the hammering thing you did is kind of insertion. No, maybe I don't know.
Maybe like actual screws or like railroad, like
gotcha.
Railroad level, production level. But actually,
why wouldn't it be able to? Because I'm sure like if you were doing a screw, the video model will generate a video of the screw going in. I guess is the issue that the robot part might not be quite right. Like you might not be able to do your inverse dynamics model.
So I think one thing is, okay, so say we want to augment data for like maybe screw driving. If we can collect teleoperation data for that task and augment data, I think it can help. But we also show new environment, new verb stuff. I think the question formulation is, can we generate new verbs, which is screw driving? But I think that's kind of right now, we do actually, fine tune the video model on like teleoperation data, right? In our specific setup, we only have teleoperation data of pick and place, but we're trying to do new verbs. I think one question left is, how do you really balance that, the adaptation phase? And right now, we also found that freezing the parameters and adding lower layers was actually critical to get like good DreamGen bench numbers. But I think there's still a trade-off where you learn the kinematics of the robot while
so if you had screwing video data in your demo set, then certainly you could generate video data of the robot. You could generate your fine-tuned video generative model could generate demonstrations, and that would be useful. But there is a trade-off between like how close it is to the final task and the amount of robot data that you really need still, I guess. That's kind of is that right? Is that your intuition?
Yeah.
Yeah, okay.
Yeah. And also, yeah. So I guess it's like the screw driving, if we fine tune on that, it's like an interpolation problem. Yeah.
Right, yeah. So like,
but I'm wondering like, how can we do the extrapolation problem with the screw driving? Is that possible? Maybe what's required for that? That's a still open question.
I mean, but maybe if I fine tune on 2 kinds of screw and I can apply it to 10 more kinds of screw, maybe that's
that
fine.
Also helps too. That also helps. But I guess, when we're thinking about the ceiling, it's about new verbs, right? We're gonna really do new verbs. So new motions, like, because the motions can be like just a big spectrum, right? So I guess,
I guess my what I'd be curious about the most would be like what the ratio is of like real data to like how many tasks it can accomplish, right? Like, and it seems like the answer isn't like infinite, right? Like clearly you need more than 100 demos that you have here, but it seems like it's probably scales pretty well, I guess, is the intuition. Okay.
Yeah, and I think that scale, once we like maybe set a scaling curve, it'll always change as the video model gets better and better. So
yeah, it makes a lot of sense.
I also want to ask, like, in the first stage of this whole pipeline, which is collecting some tally-op data so that the world model can learn the kinematics, basically what this particular, like in your case, I think for it, right, humanoid, can or cannot do. I wonder if you have tried something where you set up scene even from the initial image frame. Let's say you ask the robot to pick up something, but actually, the path to get something is completely blocked by, let's say, a sheet of metal.
Yeah.
There's just no way for you to go past.
Yeah, that's a good question.
Does a video wall model, because I imagine video wall model, even these days, they know like what is not possible. They probably rarely, but then does it translate well into, hey, given the kinematics of this, maybe another way to do is I need to retract and then, and then do this, or maybe there's just no way. Like, do you have try? Yeah.
That's a very good question. And like, it's more of a high level and kind of naturally extends to the action condition variant. So the thing about text conditions are, I think we can call it, they're positive. They're very optimistic, as in like, say in like other navigation world models, or like if it's text condition and I say, okay, show me like a yellow car, or I don't know, then the yellow car appears, even though it might not actually be there. Like, so that's an example. Like, if there's like some barrier, if it's text condition, it will do that task. That's actually the problem information itself, is doing that task. But action condition models, like, it's more control, like you can actually do it. So I think there's a little bit of a trade-off where if we really want, like, those kind of generate data of something that can't really be solved like with text alone, then I think that's where the trade-off are.
But so to flip the other side, the issue probably with let's say maybe action condition world models is that maybe it generalizes a lot less, right? Versus what you're able to do, you just put in some random verbs and then like water the flower and you kind of get that. Would you say so? When you say trade-off, it could be
and also, but the other thing about action condition is like some like maybe people, or I don't know, a policy has to come with the action itself, right? Right now we have text in. That's why it's easier to use the text condition paradigm to generate synthetic data.
Yeah, you also certainly need far more real robot data to do the action conditioned version, right? Because like it actually needs to know what the actions translate to. Whereas here, like I think one of the elegant things about it in my mind is that because you're just fine tuning an existing video model, just like obviously it can much more easily leverage all the existing stuff to generate whatever the task is. Because like it knows what, I forget, like lighting a candle looks like, right? Yeah, which is not true if your action is like rotate my shoulder joint by 3 radians. Like, that's terrible. But like, yeah, right. That's obviously not something it will have seen before in the data set, right? Like,
yeah.
I guess one observation about this paper is, which I rarely see in others, is that like the fact that within the confine of one paper, you manage to do a bunch of robotic embodiments. So it tells you there's something about whatever this pipeline they're doing, it just generalized quite easily to those. I mean, adding even just another like humanoid to the mix is completely different. Whereas in your case, well, you do the SO100 arms, and then you do Franca, and then you do the joint setup, and then you have the humanoid. So it strikes me that because the pipeline is yeah, I mean, it's fairly straightforward to add new embodiment, and that's why it sounds like it's a lot less painful.
Yes, I had more fun. Yeah. So the SC100 actually we did it like 2 days before the submission. Yeah, it's like
Gosh,
okay, so because like
okay,
Yulia
you're just
was like
rubbing
part
in
of
now.
this.
Okay, no, but it's a really positive thing. I mean, yeah. But I guess I think the last 5-10 minutes, the thing that we've been talking about is I think while these world models are extremely powerful, right, it gives really new capabilities, but then they have a lot of I think like still gaps. So it still strikes me that you probably it's still gonna be a recipe of if you really want things to work in production, you probably need a combination of a lot of other like sources of data. Could be teleop, could be like just sim data, plus a world model, maybe plus video data as well, human action on video, yeah, that sort of stuff. Yeah, but another thing I think that was interesting to me was I think IDM was from this paper that was on doing Minecraft, right? Was it?
Okay.
Yeah, yeah, and that's maybe 2+ years old. And I mean, once that paper came out, I was wondering like when will we have something that apply for robotics?
Robotics.
Yeah, so it's cool to see that it actually does work. Like help you generate those because effectively you take video and you get action, right? Even though may
Yes.
not be super accurate, but it's you can lean into the scale wherever you can generate a lot of video, whether it's streamed up by DreamGen or it could even be video data from the YouTube, let's say. Yeah, that's also very interesting. Anyway, cool. Yeah, maybe any final thoughts about like maybe future work or limitations to this work that you want to improve on your next paper, like along this line of.
Yeah, I think we covered most of the limitation and like the future work, which is like scaling. So like Chris mentioned, like, we really want to see, how like, the formula of how much still up data can enable like which capabilities. And also the biggest limitation, like the proprioception and like just other thing is the generalizability of the IDM model. Like you said, like what Michael said, like so we can this pipeline leverages video data, but right now we use the video data in the web, like human data, to pre-train the video model. Say we have a generalizable IDM. Right now the IDM is for single embodiment, but if it can extract, say, a Fourier GR1 actions with human data, I guess that can be another paradigm, but there's already other competitors for that pipeline. You can do hand pose or like, so I guess you got to show the superiority of this approach compared to that. That's just one other thing. And yeah, I think those are the immediate extensions. Yeah, future work.
Yeah, maybe as a final question to wrap things up, are there any like cool papers you came across recently you want to give a shout out to so that our people listening can also read that paper? Maybe we can invite the authors as well.
Oh yeah, I guess the 0.5 that was because like that was okay. They did open world generation. So in our pipeline, we actually take the environment, we take initial frames, and then we make that as the training data. But they showed, okay, if you have 100 environments, you can extrapolate to 101st environment. So that's like a generalization. So yeah, I think that they did for very, very hard tasks, like also mobile. So I think that's like where we should try to head towards, and maybe generate synthetic data for like these specific tasks, and also trying to diversify the synthetic data to enable a robot to actually do like one step towards open world generation. That's like a big motivation that we had.
Makes sense. Cool.
Awesome. Cool. Well, Chris, you have any more questions?
No, those are great though. Thanks for coming on. A lot of fun. Great paper.
Yeah.
Thank you for the great question.
Yeah.
Yeah, no, really, really cool, man. I think, yeah, it's well, certainly me and Chris are super excited about all this world model stuff. Like, I think our recent episodes are all world models. There's different kind of world models.
I've been seeing that.
Yeah, but yours is definitely one of the standard ones for sure. So congrats again on a great work. Looking forward to the next one, and thanks for making time again. Well, looking forward to the next one, like I said, and we'll see you soon. Okay, hold on. I'm just all right, Chris. What have you learned from Joel?
Yeah, I thought this is one of the more impressive world model papers that I've seen because of the generalization of new verbs. One of the things that I think was most interesting that we spent a while discussing was like we talked about how it kind of the usual world model formulation is like this action conditioned dynamic, at least in my mind, is this kind of action conditioned dynamics model. Like it's just a video dynamics, like action conditioned video generation, where it's like the actual robot action that it's going to take, which is not what they did. They did kind of like a reverse process where they used an off the shelf, very good video model, and then pulled actions from it. So they kind of, which is so, and it works really well at generalizing to lots of different tasks. And it's a cool paper, a lot of fun discussion. Yeah, what did you think?
Yeah, I would say works really well it definitely can generalize a lot, but then for each of the things they generalize, they are hitting maybe 20%, right? Right. So
Right.
so is it like it generalized, but 1 out of 5 times it can do that thing, right? I don't know what are the failure cases like, but so I think, and especially the chart where he had, I think the gray chart versus the blue chart. So basically, how much does having this neural trajectory help? And you realize that for some tasks it really helped a lot, but for some tasks it actually didn't help, didn't move, right? Like so.
Yeah.
So I thought that was kind of interesting. So that's why I was kind of asking Joel, like, is it just a matter of scaling? We are not past that scaling yet, and so maybe it's hard for anyone to tell right now. But
yeah, this is like we were having this discussion in the end, and I really do feel like there are some. It feels to me like there are some fundamental limitations that you have here, unless you have a good amount of robot data support for training a video model, right? Because because they are kind of relying on the robot model to solve the task, right? Which means that you need enough data that it can any time that your robot kinematics and grasping and so on intersect with the task performance, like I feel like you're going to take a hit unless you have data support for it. So like figuring out they like what he was saying at the end is like there's that equation of like how much real data do I need to get this much performance, right, to scale, like, and that is very unclear to me, right? Like you're saying, like the success rates are low, right?
And the delta for some tasks is nothing, but for some tasks is big, right? So it clearly,
Yeah.
even at this stage, can do something already for certain tasks.
Yeah. But I
So
think that's actually kind of troubling though, right? Because like the big deltas were in these semantic tasks, right? So like this is the semantic task being like the tic-tac-toe where the delta was massive. But that's one that's very easy for an image generative model, right? Because it can just like draw an X here, right? Like it's covering more of the space than the initial data was, right? And that's like, so it doesn't actually, so I feel like it doesn't reveal a lot about whether or not it can really get to like the screwing task we were talking about at the end. Like it doesn't tell us, in my opinion, basically anything about how scaling will apply to that, right? Does that make sense? I don't know. Or what do
yeah.
you think of that?
So the way my mental model of thinking about, so I think a world model just as a new class of simulation engine. I mean, it doesn't happen in the real world. It's simulation in a way. It's just completely different from the more classical simulation, like the Isaac sim and the many skills of the world, right? Where everything you basically have ground truth right in the simulation environment, where this is completely dreamed up. You hallucinate a lot, but you get some like really good qualities that you is extremely hard to get, right? He was just saying that for those folks who do simulation, it's extremely painful. For Joe, it sounds like a very fun project. He just like text generate a bunch of things. So I don't know. Like I think that whether it's my thought about simulation, whether it's a classical simulation or the world models, is I kind of feel that maybe the bottleneck eventually is because it can dream up anything in the world, but because compute is still finite. The question is what do you want the model to dream? So that setting up of what to limit the exploration space is actually the challenge. And so that's why I was asking George just now, for example, how are you? I mean, these are all text prompted, right? How are you prompting, right? So he mentioned, okay, open drawer, close drawer. It sounds like, okay, for a human, yeah, this is all you need, right? But maybe we need more. Like maybe we need to specify in text that open drawer slowly, open drawer, quickly, or maybe open drawer creatively, open drawer assuming like you get with some failure and then you recover. So it seems that like maybe even because this is text generated, so the prompt that we use, it's also the one that sets up the exploration space, right? And so we may have to be also get quite creative. I don't know, maybe ask ChatGPT, okay, give me 100 various ways to say open drawer that can be used for prompts to throw into a world model. Because that dimension of like it's not explored in this current paper, but I suspect it could be something that we need to explore also down the road.
Yeah. So I don't know. Like I agree with you mostly about like how most of the time world models papers are a data-driven simulation where you learn a model basically instead of a simulator. I am not actually convinced that is a reasonable model of this paper. Like because it is not, it's because the way that the video generation works is fundamentally different because it's not generating it like it's not it's because it's the fact that it's purely language guided and there's no process there ensuring physical consistency or even like latent space I guess it's sort of like obviously there's a latent space consistency. It just feels kind of, I don't know, I'm not sure how I feel about that. I feel like this feels slightly different to me than all of the other world models papers that we've talked about because of that fundamental difference being the fact that it's language guided instead of action guided, right? It's it's a good way of illustrating it, I guess. So like when you look at like if you try to generate something with Midjourney or Veo, right? Like you don't have the level of granular control ever, even in the best video models. I don't think I've ever seen something where I can say, like, generate a video of Chris with that painting 3 inches to the left, right? Like, if you look at my video feed behind me, right? Like, that's not something any of these models can do, like, even the very best ones. And, like, part of that is just, like, what the data distribution looks like. It's not that nothing, the annotations aren't that granular. Like, the data, there's no video of, like, 2 paintings that are 8 inches apart versus 11 inches apart. I don't know how far apart those are, right? But that kind of thing, right? And that, to me, is a huge fundamental issue if you really want to do really granular robot control, which is why I'm very curious about how much data they need to instill this new quality, basically, of being able to really finely control the ability of the robot to, like, imagine different possible futures in different, like, which is what I think you probably end up needing to do the screw driving kind of, like, really precise manipulation tasks we were talking about. So that's why I think it's, like, to me, like, it is a simulator, but it feels like if you told someone it was a data-driven simulator, I think that would give them a slightly wrong model of what it is, in my opinion. But maybe I'm being overly pedantic. I don't know. Like, is that?
Yeah. Well, I guess like
Yeah,
it's a simulation. Like in that
it
it
is.
doesn't happen
Yeah,
in the real world. It's just a very very different way of simulating the real
yeah,
world.
yeah.
And
Yeah, that's fair.
yeah,
It is. It
so
is definitionally a
yeah,
simulation, I guess. Yeah, right.
yeah.
That's fair.
But in any case, it's all good for Nvidia. So
Right.
whether it's world model or like a
As long as you're
classic
buying the chips,
simulator,
right? That's
yeah,
yeah,
it's all GPU, right?
right. Yeah,
Anyway,
yeah,
yeah, but I think really fascinating stuff, man. Like
definitely.
I can already see like the recent episodes, a lot of world models because a lot of
Yeah,
really interesting work
yeah.
being done there. So I'm
I
sure,
mean, yeah.
yeah,
Yeah. Yeah, absolutely. It feels like data-driven simulators are the future, though. Like he was talking about at the end, where how all the guys who worked on simulators are just like, it's so frustrating. It is so frustrating to work with simulators. They've got to be data-driven. We've got to figure out how to do that one, I think, personally.
yeah. I don't know whether you recall like a couple of episodes ago, I was telling one of the guys doing simulation that in my opinion, the biggest bottleneck towards like simulation scaling is you guys. Like we don't have enough of you who know what to do, how to
I
tune
think
the
that was
simulation.
Stone, right? Yeah, it's
Yeah,
got to be. Yeah,
yeah, yeah.
right.
Like we're limited by the number of like people like
Yeah,
Stone in the world, right? Who really know how to set up a simulation because it's actually
yeah.
a lot of work.
Yes,
So that
definitely.
you're not wasting GPU blindly, right? Compute
Yeah,
blindly.
absolutely. It's huge. Yeah.
But anyway, okay, cool. Yeah, I guess till the next
A lot
one.
of fun.
Yep,
Yeah,
yep.
see you.
A lot of fun issues. All right, thank you, Chris. Ciao.